Hello and welcome to a new session of physics. In today's session, we are going to start with a new topic, a new chapter basically, which is a very interesting one. I'm sure all of you would have studied this topic in your high school, and I'm sure all of you would have wondered about this topic and must have a lot of questions as students in high school. And of course, even now you might have a lot of questions, even as an adult, even as a grown-up. Even now I have a lot of questions. How does this happen? How does that happen? Right? So without further ado, let's get started with today's session. We will look at what topic are we studying in a few seconds. So to start with, how do you think this particular yogasana is helpful to us? We all know exercising is important and exercising is good for us to maintain good health, right? So doing yoga is another way of exercising. Body, mind and soul is what we call it, right? So in this particular yogasana, how do you think doing this yogasana is helpful to us? You might have come up with the answers, or you might have thought logically and answered the question such as, okay, the blood flow increases to our brains when we stand upside down. Does that mean that when we stand normally, or when we are sitting in the normal position, does the blood not flow to our brains? Of course, yes, it does flow to our brain, but as you rightly guessed, the blood flow increases when we do this yogasana, right? So when we stand upside down on our head. Why do you think that happens? It's a question to be thought about, right? Similarly, why do precipitates, you must have done a ton of experiments, a bunch of experiments in your chemistry labs, where you see there are so many precipitates that are settling down in many of the experiments, in a number of experiments, correct? So in this case, why does a precipitate settle down or immediately go down towards the bottom of the flask, right? Similarly, why do we call this one a waterfall? Why do we call this one a snowfall, right? So in this case, anything and everything, again, when we think about rain, we all usually call it as rainfall, right? So there is going to be a heavy rainfall in these regions. There's going to be lighter rainfall in these regions. So rain, when it falls down to the surface of the earth, it's called as a rainfall. Snow, we call it as a snowfall. And any dried leaves during during the autumn season, they shed, all the trees shed their leaves. They all come down. So as the saying goes, anything that is thrown up has to come down. Why does that happen, right? Why do we not float around on the earth? And why is this called as a snowfall, as we have already answered this question, right? Why don't we float around the earth, and why does anything fall? So the answer to that question is gravity. Do you look at this picture, and can you imagine that without gravity we cannot perform a very simple task? This is not even a task. As children, as kids, we must have all played slides, right? So as something as simple as sliding down a sliding surface, it is not possible without gravity, correct? So in this case, or this basically shows us how important and how crucial the property that is known as gravity when it comes to the working of things around us. So as you have as we've arrived at the topic, you guessed it right, we are going to study the chapter of gravitation. So this chapter has many interesting topics, really some amazing questions to be answered, and also the mathematical proof of the things that we learn about gravity in your high school, and also a little more than what we do it in our high school, right? So in this session, we are going to study these topics listed here. So according to my humble opinion, everything around us works the way it does because of gravity. I'm sitting here because I'm able to sit here on this chair. The chair can be placed on the ground. The table around me can be placed on the ground. It is not floating around, only and only because gravity exists, right? So why does anything fall? How do we answer this question? We answer this question because there's only one. All of the questions listed above here, everything has only one answer to it, that is gravity. So if we think about the our daily life, the things that we do in our daily lives, sitting, standing, sleeping, even eating, drinking water, writing on a paper, all of these things is possible only because of gravity, right? So can you imagine a life without gravity? Can you imagine floating around the earth without being able to walk around, without being able to jump around, dance? None of the activities that we usually perform in our daily lives would be possible without gravity, right? So in this particular chapter, to begin with, we have something called as Kepler's laws of planetary motion. So to come to think of it, is Earth the only body that has gravity? What do you think? This is a very important question to be asked to ourselves and to your teachers as well. So when you think about it, is Earth the only body that has gravity? The answer to this question is absolutely not. Think about all the planets that are revolving around the sun. Think about everything that is around you. By the way, if you looked at this picture very carefully, this is our solar system. Nothing absolutely in the universe is at absolute rest. Everything around us, everything including us and the earth that we live on, every planet in the solar system, every planet around other stellar systems, the stars in the Milky Way galaxy, other galaxy, every particle that has mass, it is revolving around some or the other larger mass with larger amount of gravity, right? So what has gravity and what doesn't have gravity? To come to think of it, or to give you a snapshot of what has gravity and what doesn't have gravity, there's nothing in the universe that has mass that cannot have gravity. By that I mean everything that has mass, it has gravity. All right. So to give you an idea of what has gravity and how tiny it could be and how large it could be, however large it could be a particular mass, such as our sun. Sun is humongously large when it is compared to any of the other planets in the solar system. That is exactly why all the planets in the solar system revolve around the sun, right? And something as tiny as an electron, which has a very negligible mass of 9.1 into 10 raised to minus 31 kilograms, also has gravity. That means everything in the universe that has mass has gravity. All right. So no matter how tiny the particle is or how large an object is, if it has its own mass, it has its own gravity. So including you and I, right? So now that we have established everything in the universe which has mass has gravity, it is time for us to understand how these things work mathematically, because you're all grown up and you've studied gravitation in your 9th grade as well a little bit. But how was it proved theoretically? All of these things would come in this particular chapter, and we are going to learn a lot of mathematics behind the working of gravity. Now, in the late 16th or in the beginning of the 16th century, there was a revolution in the field of astronomy. How is that? Because earlier than this particular time, that is 16th century, before before 16th century, it was all accepted that the earth is the center of the universe and everything around the earth basically revolves around it. Everything that we see in this night sky revolves around the earth. See, at that point, it might have seemed logical, right? Why? Because you go into an open field and you stand and you look up in the sky and you see many stars, you see the moon, you might have, if you go into very dark places, you might see a band of a part of our Milky Way galaxy as well. So you would definitely assume, for a person who does not have any other source of looking into this night sky, at the beginning it would feel like, okay, we are the center of universe. That's what Ptolemy said, and this theory was accepted for centuries until Nicholas Copernicus proposed the heliocentric system. Helio, anything that is that refers to helio, it refers to the sun, basically, right? So when Nicholas Copernicus presented this theory, and he said that sun is the center of our planetary system and everything in the planetary system revolves around the sun. However, Nicholas Copernicus, basically this laid the foundation for modern astronomy, and also there was considered to be a huge revolution, because entire theory was this was an entirely new theory, and observations also supported the same. But however, Nicholas Copernicus said that all the planets around the sun revolved in circular orbits. But centuries later, Johannes Kepler, who was working under another wealthy wise man called as Tycho Brahe, he built on Tycho Brahe's theory, saying that all the planets in the solar system revolve around the sun in elliptical orbits, and proposed the three laws of planetary motion. Now, this was the beginning, and also a very strong foundation was laid when Kepler's theory came into picture, and he proposed the three laws of planetary motion. They are laws of orbits, laws of area, and laws of time periods. So period, basically here it means the time or the duration at which a particular planet completes one full revolution around the sun. It's a periodic motion, right? So laws of orbits, laws of areas, and laws of periods. So let's look at what do each of these laws tell us. First one, laws of orbit basically states that all the planets revolve around the sun in elliptical orbits, with the sun at one of the foci. Now, you have for all of us, we know that an ellipse cannot have one center, because ellipse is like an elongated circle, correct? So it cannot have one single point as a center of it, but it has two foci being the plural of focus, correct? So what did Johannes Kepler propose as laws of orbits? Laws of orbit states that all the planets revolve around the sun in elliptical orbits, with the sun at one of the foci of the ellipse being the elliptical orbit of that given planet, right? What does second law state? Second law being very interesting, and it is also the observations also support the same. What does it state? It states that according to this law, the line joining the sun and the planet sweeps equal areas in equal intervals of time. Say for example, a planet, if there is an imaginary line joining the sun and a planet which is at point P1, let's assume that. So if in 30 days the planet P1 comes to this point, then the line joining the sun and this and P2 basically sweep area A1. If we are able to measure the same kind of area in the next 30 days, it would be equal to A1. That is what the law of areas mean, right? So what is law of periods? Law of periods state that the square of the time period of a planet, basically the orbital period of a planet, is directly proportional to the cube of the semi-major axis of its elliptical orbit. Now, if you would have come across the ellipse, of course you would have come across what is an ellipse. So ellipse basically, as we said, is an elongated circle, where if you draw two perpendicular lines like this intersecting each other, which one of the lines which is basically going through the foci, and another line which is perpendicular to this horizontal axis. The horizontal axis passing through the foci is called as the major axis. The one perpendicular to this axis is called as the minor axis. All right. So the half of these two axes are called as semi-major and semi-minor axis respectively. So semi-major axis is usually denoted as A and semi-minor axis is usually denoted as B. So coming back to the law, what does it state? It states that the square of the time period, if time period is taken to be t here, the square of the time period is directly proportional to the cube of semi-major axis of the elliptical orbit for a given planet. Sometimes we take this as this distance between the this distance of semi-major axis can be taken as capital R as well, right? So these are three laws proposed by Kepler for planetary motion, which are valid even till date. Of course, they are empirically applicable to all the planetary systems. That's how we study planetary systems in around different stars as well. I cannot call it as different suns because the sun is only one for us, right? So here is a list of semi-major axis and the period of all the planets in our solar system. Of course, Pluto is no more a planet. It is not big enough to be a planet. Nonetheless, we've included it out of courtesy, right? So as you can see, the ratio of square of time period of these planets to their cube of semi-major axis remains the same for each of these planets. Not each of these planets remains it's a constant basically for a given planet, correct? All right. So when we think about the Earth revolving around the sun or any of the other planets revolving around the sun, they are all in motion, right? So for any object to be in motion, we all understand there should be a force pushing it, correct? I'm sure all of you would have studied laws of motion and what do we mean by how these laws work, all of these things in your in your high school. So looking at the planetary system, our solar system, we all wondered at some point of time what is moving each of these planets around the sun, correct? So if each of these planets are not moving in a straight line, correct, and even if they are moving in a uniform motion, but they are still moving in an elliptical orbit which is curvilinear in nature, so there is a change in the direction of each of these planets at every point around their orbit. So there is definitely a change in velocity because there is definitely a change in direction at every point on this path. So there is definitely some amount of force that is acting on each of these planets to be able to perform this elliptical motion. So what is this force and where is this coming from? Very interesting, right? So this is the gravitational force of attraction between the sun and the other planets, all the planets which are revolving around the sun. Think of the electrons revolving around the nucleus. Where is this centripetal force required for the electron to revolve around the nucleus coming from? It comes from the electrostatic force of attraction between the nucleus and the negative electron, because nucleus as a whole has a positive charge, correct? So this electrostatic force of attraction between the negative electron and the positive nucleus basically provides the required centripetal force for the electrons to revolve around the nucleus. Very similar to this system, we have our planetary system. So in this case, what is happening? The required centripetal force for the revolution of each of these planets is provided by the gravitational force of attraction between the sun and the given planet, each of these planets basically. It is also true for moons which are revolving around different planets. Earth has one moon, Mars has two, Jupiter and Saturn have humongous number of moons as such. Basically, they are the natural satellites to these planets. So the revolution of these satellites around the Earth, around our planets, are also because of the gravitational force of attraction between the planet and the satellite. It is also true for the planet as a whole along with its satellites, and it revolves around the sun as well. It is also because of the gravitational force of attraction between a much larger body, in this case the sun, and the planets itself, right? So how do we quantify this? We don't have to worry about it because we have Newton. We have had Newton, and we still do, because of his universal gravitational law. Why is it called as universal law of gravitation? Because it is applicable for every object in the universe. So what does it state? It states that every object in the universe exerts a certain kind of force of attraction on every other object in the universe. Now, how do we quantify it, or how does this happen? What is this force? So, like how the first law of motion gives us the definition of force, the second law of motion allows us to measure this force, correct? Similarly, universal law of gravitation not only talks about or not only defines what is gravitational force, it also allows us to measure this. So how is this law allowing us to quantify this? The entire law states that, or the technical definition or technical statement of this law is, every object in the universe attracts every other object with a force with which is directly proportional to the product of the two masses and inversely proportional to the square of the distance between them. How do we do this? So if Fg is directly proportional to m1 and m2, where m1 and m2 being the two masses, it could be capital M, small m, it is just a representation, right? So what does the second part of the statement say? Fg is inversely proportional to the square of the distance between them. Combining these two proportionality relationships, we have F proportional to m1 m2 divided by r square, which can be turned into an equation by introducing a proportionality constant, which is called as the universal gravitational constant. Now, as the name states, capital G is the universal gravitational constant, and you have seen the value of it. It is 6.67 into 10 raised to minus 11 Newton meter square per kilogram square. As you have studied this in your high school, gravitational constant remains the same. The value of this gravitational constant is universally the same, no matter what the circumstances are, no matter what planet you go to, no matter what part of the universe you go to, the value of this constant remains the same. That is exactly why it is called as the universal gravitational constant. This was calculated by Henrik Cavendish, right? So how do we define, or how do we understand universal gravitational constant? So we can say that the universal gravitational constant is numerically equal to the gravitational force of attraction between two unit masses separated by a distance of 1 meter, or separated by unit meters or unit distance. All right, I'm sure you would have all studied this in your high school. Now, coming to the dimensional formula of universal gravitational constant, it can be deduced as follows. So if capital M and small m are the two masses of the two objects separated by a distance r, then G can be deduced into Fr square divided by capital M into small m. So we have the dimensional formula for the force and the dimensional formula for the square of the distance, and here we have the dimensional formula for the product of the two masses, right? So finally we get the dimensional formula for the universal gravitational constant as m raised to minus 1 L cubed T raised to minus 2. This is very important in terms of your answering any questions which is related to dimensional analysis, which is in your first chapter, right? Technically the second chapter. Now, a few things that is worth knowing about the gravitational force. One thing that you need to bear in your minds is gravitational force is always an attractive force. It is never ever repulsive. All right. Another important fact about gravitational force that is worth knowing is gravitational force is a conservative force. That is, it is always directed, or if there are two objects like this separated by a distance, and it always acts along the imaginary lines drawn between the two, joining the two centers of these objects, and it is always directed towards each other, right? Now, it is the weakest force, however, that exists among the four natural forces in our universe. Even though it is the weakest among all the four, it is the reason why the universe exists the way it is. It does. All right. So it is 10 raised to 36 times smaller than the electrostatic force and 10 raised to 18 times smaller than the nuclear force. The law of gravitation is applicable for all the bodies, irrespective of their size, shape, anything at all. Right? If they have mass, the universal law of gravitation is applicable to them because they have their gravity. Now, one more important thing to remember is gravitational force is different than gravity. Gravity is just a property of an object which arises because of its mass. Higher the mass, higher is the gravity possessed by this object, and gravitational force of attraction or gravitation is basically a force of attraction that exists between two objects by the virtue of their gravity. It is important to differentiate between gravitation and the gravity of an object. Alright, a gravitational force, gravitation can be interchangeably used because both of them are defined to be as force of attraction between two objects which have their own mass and their own gravity. Alright, there's a huge misconception that when it comes to gravity, this is only associated with the Earth. The answer to this, or the mitigation to this misconception, is that no, absolutely not. Every planet in the solar system, every star in the galaxy, and every galaxy in the universe basically has their own gravity because they have their own mass. Every tiny particle, no matter how small it is, no matter how large an object is, if it has its own mass, it has its own gravity. All right, gravity is not a term which is associated alone with the Earth itself. Now, coming to the vector form of gravitational law, we all know that the force is a vector quantity, right? It has its both direction as well as magnitude. Now, we all know what is vector. We have all studied vectors already. So this is not even a derivation as such, but it's still very, very important to understand the vector form of universal gravitational law. Now, as you can see here, we have considered two masses, m1 and m2, separated by a distance r. Now, since these are all, we are considering the vector form of universal law of gravitation, we need proper vector quantities here, correct? So, the position vector to m1 from m1 can be written as r1 vector, and the same for m2 can be written as r2 vector. So, since they are separated by a certain distance, r1, the difference between, or vector r1 minus vector r2 gives us r12 vector, which is the position vector here. So let's assume that now, according to universal law of gravitation, we know for a fact that there is a gravitational force of attraction that exists between these two objects, correct? Now, our job is to prove that the gravitational force exerted by one object on the other is exactly equal to the gravitational force of attraction exerted by the other object onto the first one, correct? So, how do we do this? Let's consider the first object of mass m1. So, the force exerted by the object m1 be F12 vector. So according to universal law of gravitation, capital G into M1 M2 divided by, what should I write here? We can write this as R12 square. Correct? I would write a negative sign here because you will get it in a minute now. So F12 is the force exerted by M1 on M2. Correct? So now when I have to write the position vector for this one, how do I write it? G M1 M2 divided by, as we know, the position vector for this one is R1 minus R2 vector. Correct? Yes. So this can be further written as F12 vector is equal to G M1 M2 divided by magnitude of R1 minus R2 the whole square into R12 cap, where R12 cap is the unit vector in the direction of R12 vector. Correct? Now, the force exerted by M1 onto M2 can be written as, we don't need this negative sign right now because R12 vector is nothing but R1 minus R2 vector. Correct? Now here there is a difference. So M1 M2 divided by R21 vector. Correct? The position vector changes because it is going from M2 to M1, right? So in this case, what happens? I would need a negative sign because M1 M2 divided by R21 becomes equal to negative R1 vector minus R2 vector. Correct? You must have studied this in your vectors when you did the third chapter, when you did motion in a plane and when you learned position vectors. Correct? Now this, so R21, again R21 cap is the unit vector along the direction of R21 vector. Now this, please do not forget the squares here. So as you can see here, F12 vector is nothing but, see, except for the negative sign, everything else is the same in equation 1 and equation 2. Correct? So I can write this as F21, and hence what did we prove? We proved that the magnitude of the gravitational force of attraction due to these two masses is exactly the same on each other. Right? So the negative sign here indicates the force of attraction or the direction of the force between these two objects. So negative sign basically tells us the gravitational force between these two objects is attractive in nature. So these two are equal in magnitude but opposite in direction. No, not really. It basically shows us the attractive nature of the gravitational force of attraction between these two objects. So this is the vector form of gravitation, universal law of gravitation. Now, as F1 and F2 are directed towards the centers of the two particles or two masses M1 and M2, the gravitational force is hence conservative in nature. Right? So we all understand, now do we all understand what do we mean by conservative forces? Right? So basically they are always directed towards each other. Right? Now let's try to solve a few questions, practice questions. So a planet moving around the sun sweeps area A1 in 2 days, area A2 in 3 days, and area A3 in 6 days. What is the relationship between A1, A2, and A3? This was a question in a very in one of the competitive examinations. It was not, though it was not very recent. These are a very similar, these are the type of questions that might be asked on the basis of Kepler's laws of planetary motion. Now the answers or the options that are given here are 3A1 is equal to 2A2 is equal to A3 and so on, right? And a few, 3 more. So how do we solve this? It's a very simple It has a very simple solution. Now we all know that according to second law given by Kepler, that is law of areas, what does it say? It sweeps equal areas in equal intervals of time, correct? So according to this, can we not write these areas as A2 divided by, A1 divided by 2 is equal to, because they are all in days, we don't have to worry about any kind of conversions as such, A2 in 3 days and A3 in 6 days. So on simplifying these ratios, what do we get? We get this as 3A1 is equal to 2A2 is equal to A3. So our answer to this question is 3A1 is equal to 2A2 is equal to A3. How did we arrive at this? Because the ratio of area swept per time taken is actually remains the constant no matter how many days it passes, correct? Yes, so the ratio of area to the period always remains a constant, and hence we have equated all of these three and we get the relationship between these three areas swept. Clear? Moving on. Another similar, important question, type of question, which again is based on Kepler's laws of planetary motion. So a satellite in a circular orbit, remember it's a circular orbit of radius r, has a period of 4 hours. Usually for our convenience, sometimes we take, in theory, we take the orbital motions as circular orbital motions. All right. So this is one of such cases. So what will be the period of other satellite with orbital radius, which is 3 times or thrice the first one, around the same planet? We are supposed to calculate the period, right, for the second satellite around the same planet, and the options given here are 16, 4 root 27 and 4 root 8. So this again is based on Kepler's laws of planetary motion, but this time it is the third law, correct? So what does the third law say? It states that the square of the period of a given planet, period of motion of a given planet, is directly proportional to the cube of the distance between the planet and the sun, correct? So in this case, it is the planet and the satellite. So how do we write this down? Can we, the basic or general proportionality relationship is T square proportional to R cube, where R cube is the distance between the planet and the star, or in this case, satellite and the planet, right? So can we not write this in this way? T1 square divided by R1 cube should be is equal to T2 square divided by R2 cube, right? Now we know that R2 is equal to 3R and T1 is equal to 4 hours, correct? So on substituting this, what do we get? 4 square divided by R cube is equal to T2 square divided by 3R the whole cube, right? So on simplifying this, what do we get? We get this as 4 square divided by T2 square is equal to, or we can also write this as, just take the periods and the radiuses or the distances on one of the sides. So 4 square divided by T2 square is equal to R cube divided by 3R the whole cube. So what do I get? 4 square divided by T2 square is equal to R cube and R cube get cancelled. So I get 1 divided by 27. Therefore, T2 square is equal to 16 into 27, right? So you go back to the options. Let's look at the option. What is our right answer? You guessed it right. Our right answer is 4 root 27. How do we get that? Simple. If I take this square off, that is, if I take the root on both the sides, I get it as T2 is equal to root of 16 is 4, and I get this as 27. That is your answer, right? Moving on. Another very interesting question. I'm sure all of you would have come across such questions while studying gravitation, right? Now, what is the question? Calculate the distance to the point between the Earth and the Moon at which the gravitational force is 0. Given that the mass of the Earth is 81 times that of the Moon, that is, capital M is taken to be the mass of the Earth, and 81 times small m is taken to be the mass of the Moon. We can just denote it in this fashion. So it always usually helps to draw a small diagram and picture it while solving such questions, right? So and the distance between them is given. It is 3.8 into 10 raised to 5 kilometers. This can be further written as 3.8 into 10 raised to 8 meters. We have just made a simple conversion, right? Now let's assume this is point P at which there is a unit mass which should not feel any kind of gravitational force of attraction by either of these two, right? So what are they asking? They are asking us to calculate or at what point or at what distance from the Earth or the Moon is that point where the gravitational force is 0. So usually this point can be defined as a null point. How do we define a null point between two masses? A given point along the imaginary line joining the centers of any two bodies at which the gravitational force experienced by a unit mass. Imagine if we place a 1 kilogram mass at this point, it should not experience any kind of gravitational force of attraction. Such point between two masses or along the line joining the centers of these two masses is called as the null point. Now our job is to calculate the distance of this point from either Earth or Moon, right? It can be done in either ways, but it is easier always to calculate the smaller distance, right? We know that the distance between our Earth and the Moon, that is this D, is equal to 3.8 into 10 raised to 8 meters. Always try to keep the units in terms of SI units. All right. Now, we know that the gravitational force of attraction can be given can be given by Universal Law of Gravitation, right? So what is the equation? Fg is equal to G m1 m2 divided by r square. In this case, for this point or to this point, how do we write this? We can write this as capital Gm divided by, what is the distance? As you can see here, the distance can be, or we can write this for the Moon itself, right? Capital this one, or capital M can be the mass of the Earth and small m can be the mass of the Moon, and we know that capital M is equal to 81 times the mass of the Moon, correct? Now capital M divided by x square, correct, is equal to Gm divided by 3.8 into 10 raised to 8 minus x square, that is t minus x square, right? Yes. Now can we convert this into a single term? So of course we can. So G into G and G gets cancelled. There is no need to write this down. So 81 m divided by x square is equal to m divided by 3.8 into 10 raised to 8 minus x square. Not x square, I'm sorry. This should not be x square. This entire thing raised to the power of 2. Let's not make such silly mistakes and lose marks over it, right? Be very, very careful. Now m and m gets cancelled. On simplifying, what do we get? On simplifying, we get this as m and m gets cancelled. So on taking the root on both the sides, we get this as 9 divided by x is equal to 1 divided by 3.8 into 10 raised to 8 minus x. On simplifying all of this, we get x is equal to, what do we get this as? So basically, on simplifying all of this, we get this as 10x is equal to 3.8 into 10 raised to 8. Therefore, x is equal to 3.8 into 10 raised to 8 divided by 10. So there is a power 1 here. Therefore, x is equal to 3.8 into 10 raised to 7 meters is the distance to the null point from the earth. Alright, so on calculating d minus x, you get the null point from the moon itself, correct? Now, this is how we can solve such simple questions. Now, if moving on, we will understand a very interesting other topic as well. We will do more of the practice questions in the coming session, and also you will have an exclusive session for practice questions alone. Subjective type of practice questions, and also the MCQs or the competitive type of practice questions will also have a separate session. Alright, so before we move on to the next discussion, here is a challenge question for you, the question for today. So when you jump, we are all pulled back onto the earth or onto the ground almost immediately, correct? So due to Earth's gravitational force. Now, do we exert any force at all on the earth during this process? It's a question to be thought about, right? Now, what do you observe here? Is there any change in the way the object is falling from when it travels from the point where it is dropped and when it moves towards the ground? Absolutely, right? There is an obvious change in the distance that it is traveling at every second or every unit of time. Why does this happen? Now, when an object is not covering a uniform distance or the same distance in same intervals of time, what do we call such a motion as? We call this as a non-uniform motion. So how do we define non-uniform motion? You all know this. Non-uniform motion is a motion in which an object covers unequal distances in equal intervals of time, or vice versa, correct? So in this case, it is covering larger distances as and when we measure it, for every second or every unit time. So what is that parameter that is changing here? So when an object is it is said to be in non-uniform motion, it is the velocity of the object that basically changes. So for a velocity of the object to be changed, what needs to be there? When is that we say an object is changing its velocity? When we say the object is accelerated, correct? So when will this acceleration in an object come into picture? Only and only when there is a force. Now, when an object is thrown up and it is coming down, why does it accelerate? Because there is a force of attraction acting on it, correct? Which is very obvious, which is the gravitational force of attraction. Now, when any object experiences a gravitational force of attraction, which is, and it is in the direction of the motion, right? So when I drop a particular object from a certain height, it basically falls towards the earth, correct? So here, in this case, what is happening? The Earth's gravitational force is is vertically downwards. The object the direction of the motion of this object is also vertically downwards. Since the force is acting in the direction of the motion of the object, the velocity of the object increases. In other words, it gets accelerated. When an object is thrown upwards, what happens? The gravitational force of attraction will be the direction of the force does not change due to gravity, correct? The gravitational force of attraction is always vertically downwards towards the center of the earth, right? You have studied this in your high school. Now, when this happens, when an object is traveling in the direction opposite to the force due to gravity of the earth, what happens to it? It is pulled back, right? Even though there is an applied force that is pushing it, that is basically while throwing it, we give it certain amount of velocity to go upwards. It is constantly pulled down because the gravitational force of attraction is acting opposite to the direction of the motion, and hence the velocity constantly decreases and the object experiences a negative acceleration or deceleration, right? So the force exerted due to the Earth's gravity on a given object which is falling towards the Earth, it's the only force it experiences, correct? So this particular scenario, this particular fall is called as a free fall, because there is only one force that is acting on this object, that is the Earth's gravitational force. And the acceleration that is produced in this body due to the Earth's gravitational force of attraction is called as the acceleration due to gravity, and we all know this term, small g. I'm sure you would have studied this in your high school, and we have all had instances where we would have interchangeably used acceleration due to gravity, small g, and the word gravity itself. Please be very careful not to interchange these two words, because their meanings are humongously different. Gravity is just a property. The measure of gravity of a given object is given by the mass and the gravitational force of attraction it exerts on any other object. Of course, according to Universal Law of Gravitation, the gravitational force of attraction exerted by one object onto the other is exactly equal to the gravitational force of attraction exerted on the first object by the second one. That is what we proved. F12 is equal to F21, correct? Yes. So acceleration due to gravity, small g, and the word gravity are completely different. Please do not interchange these two. And gravitational force of attraction and gravity are also different. It's very imperative. It's imperative to understand and bear in our minds that these three quantities or these three parameters are very different from each other, one another. Now coming back to small g, again acceleration due to gravity, small g, is very different than the capital G, which is universal gravitational constant. So we have learned that the Earth attracts object towards it. This is due to the gravitational force, and the acceleration produced in an object due to the gravitational force of attraction by the Earth or any other planet that basically is exerting a gravitational force. It does not mean that if I go onto the Mars and if I drop an object, it will just float away. No, it will come down, but it's just that Mars is smaller than the Earth and hence has lesser amount of mass, and hence the force exerted by Mars onto this object might reduce, and thus the acceleration due to gravity on Mars might have a different value. Not might, will have a different value, right? So it is, the acceleration due to gravity is a vector quantity. It changes with the places. It does not remain constant all over the planet. It is just that we take the average value of acceleration due to gravity as 9.8 meters per second square, right? So this is a vector quantity and it varies from place to place. So whenever objects fall towards the Earth under this force alone, we say that the objects are in free fall. Acceleration due, and such objects have acceleration due to gravity, which is a constant value. So basically they are moving towards the Earth with a uniform acceleration. When an object is thrown upwards, they are moving upwards against the influence of gravity with a uniform deceleration or negative acceleration, right? Now let's try to deduce a relationship between acceleration due to gravity and the universal law of gravitation. Now say for example an object of mass m is under free fall. That means basically it is attracted towards the Earth, right? So when the when we compare the radius of the Earth and the distance at which the object is kept, or let's just assume that the object is kept here, or which object is moving towards the Earth here. So this distance is basically negligible when it is compared to the radius of the Earth itself. So let's say the mass of the Earth be m, that is capital M, and mass of the object be small m. Now this is falling towards the earth with an acceleration, uniform acceleration, small g, which is equal to, or which is taken to be on an average as 9.8 meters per second square. Now, according to universal law of gravitation, F is equal to, what will it be? It will be capital G small m into capital M divided by r square. Let's keep this as equation 1. Now, we also know that any object which is acted upon by a force, according to general equation of force or according to second law of motion, we can write the same force as mass of that object, and this is basically we are writing the equation for the force acting on object of mass m, and acceleration produced in it is g in this case, correct? So this is equation 2. Now, if you observe carefully or if you think about it carefully, these two equations are representing exactly the same force. So why don't we equate it? Let's do that. mg is equal to g into capital M small m divided by r square. Now, since these two are the same terms, they get cancelled. So g is equal to capital G into capital M divided by r square. This is the general equation for acceleration due to gravity for any object. So we know the mass of the earth, we know the mass of the we know the radius of the earth, and we know the value for capital G. Can we not calculate the value for small g, that is acceleration due to gravity? Using these terms, if we do the calculation, we get the value of g is equal to 9.8 meters per second square as the general value, that is accepted value for acceleration due to gravity. Now, we all understood what do we mean by gravity, what is gravitational force. In this particular session, I think we laid a strong foundation to study further, a slightly complicated, theory of how objects work around the earth. What is the mathematics behind the revolution of a satellite around the earth, or earth around the sun, or moon around the earth. All of these are coming up in the further sessions. Let's just quickly recap what did we do in today's session. We understood the meaning of gravity. We understood what do we mean by gravitational force and how these two are very, very different from each other. We learned Kepler's law of planetary motion, the three laws, law of area, law of periods, and laws of orbits. We also did a few practice questions. We understood how do we deduce, or we proved using vector form of universal law of gravitation, saying that any two objects, or if we are to calculate the force of attraction between gravitational force of attraction between two objects, they exert the exactly same amount of force onto each other. And we also understood what do we mean by acceleration due to gravity. It is entirely different from the universal gravitational constant capital G, and also the word gravity. It is different from acceleration due to gravity and the word gravity are not the same. They are entirely different. So, and also we deduced a relationship between acceleration due to gravity small g and the universal gravitational constant capital G. We also understood the meaning or physical meaning of capital G, that is universal gravitational constant. It is nothing but numerically equal to the force of attraction between two unit masses separated by a unit distance, right? So with this, we come to the end of today's session. In the next session, we have a lot more coming up with a lot of practice questions and a lot of interesting theories. Till then, thank you and bye-bye.